This video gives some practical tips in how to find the angular momentum for a given system with a given motion. Maybe it should be entitled something like, all you need to know about getting the L. So what's the angular momentum for a single particle? This is the definition of angular momentum. The particle is moving here. There it is. It's moving with some momentum. And now we don't have any meaning for the idea of angular momentum until we specify an origin, which is this one here we'll take. And now the angular momentum is given by the vector cross product of the vector from S to the mass, or to the point, the particle, and it's multiplied by the vector for the momentum. So that's what you need to know to find angular momentum in 3 dimensions. That's the definition of angular momentum, and if you have a complex system that is a number of different point particles, or if you have a rigid body, which you can consider as a number of individual mass point particles, then you just add it up. You add up the angular momentum for all those things, and that's the angular momentum for the system. Now usually angular momentum is dealt with for 2-dimensional systems in introductory mechanics. That is, the momentum and the point S that you are talking about and the particle all lie in a common plane, in which case you're really finding the z component of the angular momentum. And just like the torque, the z component of the vector product is found from the relationship that Ls equals plus or minus the magnitude of that vector r of the displacement from the point you want to find the angular momentum, about S, to the point P where the momentum is, or the particle is, times the momentum of the particle times the sine of the angle with the sign convention, and that's the angle between R and P. And basically there are 3 easy ways to find that angular momentum. The first is the tangential component of the momentum. The second is the moment arm of the momentum about the point S. And the third way is the geometric way plus the sign convention, which is in this expression here is the geometric way. So those 3 ways to find the angular momentum are for planar motion in 2 dimensions, where you're basically evaluating the r cross p for a single point particle moving with momentum p and a distance r from the point S about which you're finding the angular momentum. Now let's consider a special case, which is that of a fixed rotating disk, and it's rotating about the center of mass. So this is the point we're going to find the angular momentum. And the way we're going to find the angular momentum is by remembering that the angular momentum for a complex system is the sum of all the moving masses. And so we're going to consider a little piece of mass like this little delta m here, and ask, okay, so what it's doing, let's find its angular momentum. And it's rotating about the fixed axis, and it's rotating with angular speed omega, and so it rotates with the speed omega r. This little vector here is the velocity of the particle, and it has mass delta m, and it is a distance r from the origin, and so it contributes delta m omega r squared to the angular momentum. Now the disk, of course, is made of many of these little mass elements delta m, so if we have to add them all up to find the angular momentum about the center of mass. And we therefore get this sum here times omega, because every one of them is proportional to omega. But if you remember, this is the definition of the moment of inertia. So basically the angular momentum of the disk, due to its rotation about its fixed center of mass, is I omega. And we have to, I have a plus and minus sign here to indicate you have to think about the direction of rotation, and that we use this plus sign here, convention for counterclockwise rotation, and therefore we would just have a single plus sign there for the expression in this particular case. Okay, now let's assume that we have a disk that is moving, but that it is also rotating. And so now we have to basically add together 2 ideas. We know from the angular momentum of a point particle that even if the mass were all concentrated at the center, it would still have angular momentum the same as a single particle. But in addition to that, it's a rotating disk. And so we say that the system here is both moving with velocity v center of mass. So maybe I should write that in, v center of mass. And in addition, it's rotating with the angular speed omega. Adding the angular momentum from those two motions together, then we come up with the formula that the angular momentum about point S is r cross p, or that term, plus or minus I about the center of mass. And this should turn into the most useful formula for a general rigid body, where we don't evaluate the r cross p, but we just look at the z component of that, and therefore the most general formula for two-dimensional motion of a system that's moving with velocity v and it's rotating at omega, and this is basically, remember, this is 2D, is plus or minus r center of mass times p times sine of the angle plus or minus I center of mass times omega. Sometimes this is called the orbit term here, and sometimes this one is called the spin term or the rotation term, because it refers to the body rotating. Finally, let's look at a very specific case, a very limited case, which is that the axis is fixed and the system is rotating not about its center of mass, but that the axis is some other place than the center of mass. So the center of mass is up here, and we're trying to find the angular momentum about point S. Well, we can start off by using the same formula that we just found for the general rigid body moving, and that's this equation here. And so we have to figure out, well, how is it actually moving? Well, since the axis is fixed, then the velocity of the center of mass is coming up here like this, and it's equal to omega, the rotation rate about there, times this distance d. So that can be substituted into the formula for the momentum, which is m times the velocity to the center of mass. And so we can go about this thing by saying we have the term dm times v center of mass. This term here is from the motion of the mass at the center of mass, plus I center of mass times omega. Now, if we put the value in for the velocity, then we see that the velocity is omega times d, and now we get this md squared times omega, and now everything is proportional to omega. So we can factor that out, and we have that the angular momentum about point S is md squared plus I center of mass. Well, if you remember the formula for the parallel axis theorem, then you see that this is the angular momentum is equal to I about S, the moment of inertia about the point S, times the angular speed of rotation of the whole thing. But this formula, which many students just love to use, is really only valid in the special case that the axis is fixed and that it is not at the center of mass. So it really has rather limited applicability. And in fact, we can regard what we just did as a derivation of the parallel axis theorem.